Okay, so this problem reads, the speed of propagation of the action potential, which is an electric signal along a nerve in your body, in a nerve cell, depends inversely on the diameter of the axon, so how big the axon fiber is. If the nerve cell connecting the spinal cord to your feet is 1.1 meters long, and the nerve impulse speed is 18 meters per second, how long does it take for the nerve signal to travel this distance? All right, so we're dealing with kinematics kind of here. How long does it take for something to travel? What time is that? So we'll follow our kinematics process. The first question we ask is, what is that object? Well, the thing that's moving is that impulse. So that nerve impulse is the object we're interested in. When do we start caring about that impulse and when do we end? What defines our initial and our final? Well, we start caring when it starts at the top of the leg. So it tells us, remember, that it goes from the spinal cord to your foot. Your spinal cord's in your back. So at the spinal cord is when we start caring, and we stop caring once it hits our foot. So that's when we don't care anymore. All right, so we need to draw a picture. So here is our person, and we'll say that the nerve impulse is going to start at the spinal cord here. So we'll call that spinal cord location our origin. All right. One-dimensional motion, that dimension is straight down. So we have our initial and final positions, our initial and final velocity, our acceleration, and our time. So it starts at the spinal cord. We've defined that as the origin. It ends at the foot, and it tells us that from the spinal cord to our foot is 1.1 meters. So that's our final position. Negative if I'm moving downward. Okay. Our initial speed, it says that it has 18 meters per second is the magnitude of that impulse. And again, it's traveling in the downward direction based on my picture. And I've identified that direction sort of by convention. So positive is up, negative is down. We're moving at a constant rate, so our final velocity is the same as our initial velocity, and there is no acceleration. And we're interested in how long that takes. All right, so our list of known values. We then ask ourselves, what is the variable of interest? Well, we're interested in how long does it take. Now I have two equations that use time, and one uses initial and final position, which I have, and initial velocity. The other is dependent on acceleration. So we're going to use our position equation, recognizing that because I do not have an acceleration, that last term goes to 0. And that can be rewritten as our final position is equal to our initial position plus our speed, velocity, times time. So our final position is negative 1.1. Our initial position is 0. Our velocity is 18 meters per second times our time. So 1.1 divided by 18, and we get a time equal to 0.06 seconds. Pretty short to get that impulse from our spinal cord down to our foot. Right, recognizing the object, identifying what starts the motion, what ends the motion, making sure we identify that origin, our players, picking that right equation, what's going to get us to the answer, and then solving. Good job.